Start recording. Okay, welcome back to Organic Chemistry 2330, Introduction to Organic Chemistry. We're going to continue on with Chapter 7. And what I would like to do is actually finish with Chapter 7. So if we finish a little early today, that's okay. And we're going to work on Chapter 6 all next week, okay? I was warned that Chapter 6 and Chapter 7 homework actually weren't assigned yet, and so they are currently assigned on Top Hat. So those should be available to you. Next week, I'll talk a little bit more about the exam. The exam is going to be multiple choice. It's going to be a Top Hat. You must have Top Hat to take it. I'll give you instructions, and I'll also send out an email of instructions for that exam that is going to be on Thursday, February 25th. Okay, Thursday, February 25th at this scheduled time. We're going to just, instead of logging in here during our regular class time, you're going to log into Top Hat and take the exam. Okay. So that being said, let's go ahead and share my computer. And does anybody have any questions about that right now? Okay, I'm going to go ahead and share my screen. Okay, let's see, where did my shared screen pop up? It's not there, it's not there. Okay, there we go, right here. All right, so I got shining faces over here, nobody's in the waiting room, and the shared screen is there. Can we see the shared screen? Yes?
Yes.
Great, thank you. Okay, so what we did in the last thing is we looked at alkyl halides as leaving groups. That's the whole point right there. And so they can either leave ahead of time and form a carbocation, which is what our SN1 reaction was. And SN1 reactions are dominated by the fact that you have to have a stable carbocation. So it's only secondaries and tertiaries that'll do this. However, if it was a secondary, you had to have a protic solvent with a poor nucleophile to support that charge. The other way that we can have a alkyl halide or a halogen leave the molecule is to come in from the backside and kick it out. And then we call that an SN2 reaction because it took two molecules, one bond making and one bond breaking at the same time, okay? Now, this is dominated by sterics. So if you have big bulky groups like a tertiary, it does not happen. Although it can happen on an SN2 if you have a non-polar, non-protic solvent, so it won't support a charge, and really good nucleophiles. It'll come in and attack it. Then, of course, the primaries and secondaries, that's their main reaction they do, is that substitution reaction by bimolecular, because there's nothing blocking the way. Okay, so that's one way to remove halogens from our system. That's one way they're a leaving group. But there's another way they're a leaving group, okay? And that other way is to actually have it leave with a hydrogen. So you imagine you're taking a halogen and a hydrogen. You're taking away an acid, right? HCl or HBr. We're taking away an acid, okay? And in those cases, we're called an elimination reaction. But remember, the carbon that the halogen's on is called the alpha carbon, but you have to have a hydrogen on the carbon next to it to remove it. So that's why we call it beta elimination. So you'll see here the little beta is missing from the symbol over here, but it's beta elimination. Okay, that means you have to have a halogen on your alpha carbon and you have to have a hydrogen on your beta carbon to completely remove acid. And what reacts with acids? Bases. So we're going to do these beta elimination reaction using bases. Okay, when we do that, when we remove the hydrogen here, the electrons stay behind and create a pi bond, and then you end up getting your byproducts on the system. So in beta elimination, we're creating that double bond between two carbons. Okay, so we in the substitution reactions, we started with an sp3 hybridized carbon and we ended with an sp3p hydrocarbon. In beta elimination, we actually have to convert hybridization to sp2, and we get that nice trigonal planar structure and that pi bond above and below that sigma. So let's start talking about that, why you might want to do this and why it might happen. So the first thing we want to do is we want to say that the products we get from this beta elimination here is that we are going to try to form the most stable alkene possible. Okay. Now, remember when we talked about alkenes, the most stable alkenes are the ones that are either more substituted or the trans configuration. When we talked about alkenes and alkynes, we looked at that by the heat of hydrogenation, told us which compound was more stable because less heat is given off in a more stable hydrogenation. So in the case of our compound here, we have a tertiary bromine, so it's not going to react with an SN2 reaction. But in the presence of a strong base, it will eliminate one of the hydrogens. And we have a couple different hydrogens available here. I'm going to draw a hydrogen on this carbon here, over here, and I'm going to draw a hydrogen on this carbon over here, and I'm going to draw a hydrogen on this carbon over here. Okay. Each of those carbons is a beta carbon, and each of those hydrogen is a beta hydrogen. We have to have our halogen on our alpha and a hydrogen on our beta. Now, what happens if we eliminate this hydrogen here? Well, we end up with a double bond being right here. Okay, so that's one possible way to do it. And if we took this hydrogen off right here and the bromine, we'd end up with our double bond here, which gives us actually the same structure. It's just flipped over. Okay. However, our last section here, this red hydrogen here, that's going to give us a different product because that's going to give us our double bond where it's over here. And notice this double bond has 3 substituents. This double bond has 2 substituents. So based on that argument, because we are going to give the most substituted alkene, this is going to be our major product. And the rule is called Zaitsevs Rule. Zaitsev says you are always going to form the more stable product. The more stable product is the more substituted. And if you have a cis and trans possible, it's always the trans isomer. Okay. Hitting the green tea a little early today. Okay, so let's apply that again to the next compound here. So the first thing we have to do is remember those beta hydrogens. Okay, so those beta hydrogens are, we have one beta hydrogen here, we have a beta hydrogen here, and we have a beta hydrogen here. Okay, because they're symmetrical right here, I'm calling these 2 beta hydrogens exactly the same. And so those blue beta hydrogens, we're only going to give the same product. But if we have this red beta hydrogen, that's going to give a different product. So what that's going to do is that's going to give us that double bond in between where the bromine came off and the hydrogen came off, giving us our double bond outside the ring, and it's only di-substituted. Okay. However, if we take the blue one right here, that's going to give us our double bond here and give us our tri-substituted double bond. And therefore, it's actually better to form the more, the small ring with the double bond in it than to have it be outside the ring here because it's more substituted. Again, following Zaitsevs rule. Okay, so beta elimination, always look for your hydrogens and where they are because you can have different isomers depending on which hydrogen you take off. Okay, so in beta elimination, there are actually 2 competing mechanisms, just like in the substitution reaction. And the 2 competing mechanisms are called the E1 mechanism. And in the E1 mechanism, we actually form a carbocation first, okay? So it's unimolecular. So just like in SN1, you have to form a carbocation. In E1, you have to form a carbocation. You have to break a bond first and then remove the hydrogen second. Okay. And in contrast, in an E2 mechanism, what you have is the base comes in and starts tugging on the hydrogen first, and then the electrons kick in and that kicks out. So it's bimolecular, the base is involved in the system. What that means is that the rate is only dependent on the concentration of the halogen in the first one, where the halogen, only the substrate with the halogen on it, because that's the slow step. That we have to wait for that halogen to come off before anything else is going to happen. In contrast, when we have the base coming in and interacting with the alkyl halide, then it has to involve both the concentration of the alkyl halide and the base. So we can make the reaction go faster by adding more base in those types of reactions. Okay, questions on the concept of beta elimination?
So these mechanisms are basically the equivalent of the SN1 and SN2 ones, correct?
Well, the analogy I want to say is that the E1 means that is like the E2, and in fact, you form a carbocation. The E2 and the SN2 have to have two different molecules coming together and bonds breaking and leaving at the same time. That's the similarity between the two ones. In the SN, in the substitution reactions, we always end up with sigma bonds. In the elimination, the beta elimination, we end up with an alkene. Okay, so that's kind of the compare and contrast of the two. Does that answer your question?
Yes, thank you.
All right. Okay, so let's go into where things happen. Remember, we only have 4 things that can happen. I'm sorry, 5 things that can happen in a mechanism. So we're going to look from one of the ones that has to happen in an E1 reaction is we have to form that carbocation. So the first thing that has to happen is we need to break that bond to give a stable molecule or ion. Okay, so what happens is our electrons pop out from that sigma bond between the carbon and the bromine, and that gives us our carbocation and a counterbalancing counter ion. Okay, now remember that this right here is a weak base, so we need to remember that that happens. Okay, now the next thing that has to happen is we have to remove an alpha hydrogen. Okay, so, or an alpha proton. So in this case here, we actually have a symmetrical molecule. So really all 3 types of alpha hydrogens are exactly the same. So it doesn't matter where we take it. Okay, now in this case, we're also using another poor base. We're using methanol. The lone pair on the methanol is acting as a Lewis base, and it's reaching out and putting those electrons onto that hydrogen, breaking the bond between the hydrogen and the carbon. And those 2 electrons are the 2 electrons that move over to form our double bond right here. So we took the electrons from that carbon-hydrogen bond and turned them into a double bond. And in the process, we created an acid here, this oxonium cation. So that means the next step might be to have an oxonium ion react with something so it regenerates the base. Okay, in contrast, the E2 mechanism happens all at the same time. So what you want to do is you want to have probably a strong base come in and start tugging on your hydrogen first. And when it does that, it comes in with its electrons, starting to form that bond with the hydrogen. That's liberating these other electrons to come over and switch in and get in between those 2 carbons. And when it does that, now we can have the electrons leave on the bromide ion. So we generate a neutral species and the bromide ion plus our new double bond. Okay. Now, again, this is a symmetrical molecule, so we only have 1 type of alpha hydrogen, so we only get 1 isomer. Okay. All right, questions on the E2 mechanism. Okay, so think E1 carbocation and all its problems, right? The carbocation has to be stabilized with a good solvent. It can rearrange, and which side that hydrogen comes off is unknown. We don't know where the hydrogen is going to come off, but we do know we're going to form the most stable double bond possible. In this case here, we can actually have certain different parts of these alpha hydrogens can do different things. So we're going to have to look for changes in our E2 mechanism by what different groups we have. Okay, so in general, primary alkyl halides do not undergo E1. Why? If the first step in E1 is forming a carbocation, primary carbocations are not very good. So we're not going to do an E1 in a primary alkyl halide. That means that we must go with E2, which means we have to have the hydrogen being pulled off at the same time the halogen is leaving. Okay. Now, in the case of the secondary, it can react E1 if we have a weak base and a protic solvent. Notice that in this case, water and alcohol are not only a solvent, but they also act as weak bases. So if we had a secondary halide in a water and alcohol, think of an E1 reaction where you're forming your carbocation and it's stabilized by that protic solvent. In the case of if you have a very strong base, you already have your negative charge there, it's more likely to undergo an E2. That base is already there. It can tug on one of those hydrogens and make it happen all at once. Okay. In a tertiary right here, the main reaction is the same thing with a weak base. In fact, you can even use a weaker base because the tertiary carbocation is very stable, so that it is likely to form under both conditions. So, and then with a strong base, it'll also undergo that. But it easily forms those tertiary carbocations, so it can undergo either mechanism depending on how strong your base is. Okay, so in substitution reactions, we were talking about the strength of the nucleophile, and whether it was a strong nucleophile or a weak nucleophile. In elimination reactions, is it a strong base or a weak base? That's what we're looking for here. So they can be the same, but they're not always the same. So we need to pay attention to that. Okay, so because nucleophiles are also strong bases, that means that we have a competition between the substitution reaction and the elimination reaction. Okay, so in the case of this alkyl halide, if we have a nucleophile that's acting as a nucleophile, we get substitution reactions, and we get our 4 bonds to carbon in our system, and we eliminate our halide here. If our nucleophile instead acts more like a base, it'll come in and remove the proton from the other side, kicking the electrons in, giving us our beta elimination reaction. Okay, so how do we know the difference? Well, let's look at some examples and think of things that are classically basic versus classic nucleophiles. All right, so in the case of, okay, and so that is a primary right there. Let's look at secondary and tertiaries as well. Okay, so in the case of these compounds here, we have either out the iodine or the chlorine can leave to give us our carbocation. Remember, it's an E1 reaction. And in the case of SN1 or E1, the first step is always forming the carbocation. Okay, so let's say we had a base in there somewhere. We could eliminate that to generate our alkene and give our E1 mechanism. Okay, now in the case of having something like a very weak base, like water right here, we can get that substitution reaction to happen. Or in the case of this, also a weak base, it will act as a nucleophile and create a new compound, which is our ether. Okay, so we start seeing there might be a trend of possible products, but we should be able to differentiate between the SN1 mechanism and the E1 mechanism based on basicity and the nucleophilicity. So we need to compare and contrast those two things. Okay, so with another thing in our SN2 and SN and E2 is the fact that because we have the base coming in, tugging on the hydrogen on the beta carbon and the leaving group on the alpha carbon, they have to be oriented correctly such that we can make this happen. And so what we'd like to see is the hydrogen that is going to be anti or completely opposite of where the leaving group is, that leaves it the ability for the electrons to kick in and kick out. Okay. So if we can rearrange our material such that we have that hydrogen on, notice this hydrogen is like completely opposite where this is. And so these two R groups are aligned, these two R groups are aligned, and the hydrogen and the leaving group are parallel to each other. If we can orient our molecule in that, that's going to tell us when we form our double bond, these two R groups with the solid wedges are coming out at us are going to be on the same side. And these two blue R groups that are heading back to it are going to be on the same side of that bond. So we have to not only make a double bond, we don't actually also have to figure out which double bond is more stable, but in an E2 reaction, we have to see where this hydrogen is to see the leaving group. Now, what do we have when we do an SN2 reaction? In SN2 reaction, we have our nucleophile, and I'm going to put it in green here, coming, and it has to come and hit the opposite side of the leaving group, right? Because it has to form the bond and break the bond at the same time. So notice if we're having a base or a nucleophile, we're all coming in from the same side of that alpha carbon. Okay, so if we're paying attention there, that's going to give us two different products, and our R groups are going to be kicked out here. I'm sorry, our R groups are going to be kicked differently in the SN2 reaction compared with the E2 reaction. Okay, so how do we tell them apart? Okay, here's some rules. Okay, these are the rules for telling it apart. First of all, a methyl halide cannot undergo elimination reactions because there are no alpha hydrogens. Okay, so a methyl halide will undergo an SN2 reaction. Okay, it only undergoes an SN2 reaction because it has no ability to form a carbocation, so it can't go in SN1. It has no alpha hydrogens, so it can't undergo an E1 or an E2. So that means the methyl halogen can only do one thing. Okay, now the primary, which is where we have that methyl halide, but it does have the opportunity to have alpha hydrogens, gives us a couple more things to happen. First of all, we're gonna have that SN2 reaction because again, it's going to give us a primary carbocation. So we don't want to form a carbocation. So we're gonna have that SN2 type reaction. And this reaction happens when we have strong bases and strong nucleophiles, okay? Because this is a strong base and this is a strong base, but it can easily come in from the backside and kick out the thing. It's more likely to act as a nucleophile, okay? And the things that aren't very basic, like iodine and acetate ion, but are still good nucleophiles, will also come in and do the substitution reaction, okay? That means to get an E2 reaction, we have to have what we call a big, bulky base. And our classical big, bulky base is called T-butoxide, potassium T-butoxide, okay? And what that looks like is you've taken tertiary butyl alcohol and removed the proton and you put a potassium here. Do we see why that's a big and bulky base, okay? This is so big hydrodynamically, it cannot act as a nucleophile. It can only remove protons, and therefore it is used exclusively here to make this E2 reaction happen. Okay, and of course it doesn't form carbocations, so it can't do SN1, SN2. So the methyl has one reaction possible. The primary has two reactions possible. Both of them are bimolecular. Okay, any questions on that? Now we're going to get, of course, secondaries we know are going to be complicated because they have a variety of things that can happen. Okay, so in the case of a secondary, of course, if you have weak bases and strong nucleophiles, things like iodine and acetate ion, it's going to act as the nucleophile because they're not very basic. So it's going to give you the substitution reaction, and it's going to give you the SN2. If they're a good nucleophile, you will get an SN2 reaction. Okay. However, if you have a strong base and strong nucleophile, something like hydroxide or alkoxide, you're favoring an E2 reaction. That strong base is going to pull off an alpha hydrogen and eliminate, giving you that secondary, giving you that double bond. Okay. But If you run it with a very weak nucleophile in a protic solvent, like you just boil your secondary alkyl halide in water or methanol or ethanol, you are actually going to have competing reactions. You're going to have some of it undergo an SN1 because it's going to form the carbocation, and then it can react with the water or the methanol to form a new carbon oxygen. Or it can, the water, methanol, or ethanol can act as a weak base and actually eliminate. So typically when we have a secondary alkyl halide, you're actually going to get both products. You're going to get your substitution product and you're going to get your elimination product. Okay, so any questions on that? Okay, so the words we're looking for is weak base, right here, weak base, good nucleophile, substitution, strong base, good nucleophile, elimination, weak base, weak nucleophile, formation of a carbocation, and a competition between SN1 and E1. Okay, so let's go to the tertiary. That's the last one right there. And we know it doesn't undergo SN2 reactions because it is extremely crowded. It's a sterically controlled reaction, so we don't see it. Okay, so that eliminates that, and that makes it easier. So we don't do that one right there. But we do have the E2 available to us because if there's a hydrogen that is on a beta carbon, that means the base is further away from the alkyl halide, and it can still pull that hydrogen off, have the electrons kick in, and have the bromine kick out. So this usually happens when we have strong bases, okay? So we're not worried about nucleophiles anymore, but we're looking for our strong bases, things that already have a negative charge on them, okay? And if we have a polar solvent, we can have weak nucleophiles and weak bases, and we'll have a competition between the E1 and E2. And so what's going to happen is you're going to form your carbocation, and then it's either going to pull hydrogen off or it's going to substitute at that carbocation. Okay, questions about those? Okay, so let's work through those rules one more time and try to figure out what our major products might be, okay? So first thing we're going to look at is this top one here. And then this top rule here we have, well, we have a tertiary, okay? So that's a tertiary. So that means we're going to form a carbocation. So that means it's SN1 or E1. Those are our only two choices, okay? Now, when we talked about our SN1, E1, we talked about the idea that it works if it has a good nucleophile. It will do for that, a strong base will do an elimination reaction, but a weak nucleophile or a weak base will do the substitution reaction right here. So there we go. So we're looking for what we have, and what we have is a strong base in a protic solvent. So we can support our carbocation here, but we cannot support our substitution reaction. Even though water is a weak nucleophile, we have a presence of a strong base, and that strong base is going to give our elimination product. Okay, so let's figure out where our elimination products are. So we have to draw our alpha hydrogens here. We got that alpha hydrogen, which would be the same as the other carbon here. And we have another alpha hydrogen right here. So we're going to have two products because we have two different types of alpha hydrogens. So the product for our alpha hydrogen with the red one is going to give us our double bond here and give us the rest of the material. So we're going to have our double bond, and then we draw the rest of the line. So that's one possible product. In the case of our pulling off our hydrogen here, these electrons are going to kick in, giving our second possible product, which is that one. Now, of the two, which is going to be the major product?
Probably the blue one.
The blue one, because it is more
More substituted.
Yes, right. So the first few times you run through this in the homework, go ahead and try to figure out where those alpha hydrogens are. I'm sorry, the beta hydrogens are. Draw the beta hydrogens and see if they give different products. Because you'll see that this right here, it's going to give the same product as the red one. But that blue one gives that more, gives that major product. And this would be the correct answer on the homework. All right, now let's look at this next one. We have a primary, okay? So our primary can only undergo SN2 or E2, right? Never forms a carbocation. So what are the conditions? Oh, we have an amine. We just talked about amines, right? And we know that they are weak bases, but they're base. They're not, they don't have a negative charge on them, so we're going to call that a weak base, okay? So we have a base, but it's also a poor nucleophile because it doesn't have a charge. So I think it's going to undergo an elimination reaction because of the fact that this right here, the triethylamine, is a base. Okay, so let's draw where our alpha hydrogen is. We have two beta hydrogens right there, and it's going to give us one product. Okay, and our one product is going to be that. Okay, notice it's not the more substituted one, but it's the only one we have available to us because we only have one type of beta hydrogen. Okay, now the next one I think is going to get complicated because it's got a secondary. But let's go through our options and figure it out. Okay, so we have a possibility of almost anything because it's a secondary right here. Okay, but we have a clue. We have a protic solvent. Okay, so I'm thinking it's going to be an E1 or an E2, an E1 or SN1 reaction because we have that protic solvent to help support. Okay, and look at this. We have a strong base and we have a good nucleophile. Okay, so we have strong base and good nucleophile. So we're going to have competing SN1 and E1 reactions. And where are we going to do it? Well, let's draw an alpha hydrogen here. So it looks like the two different places we can draw alpha hydrogens are equivalent. So that means we can do one either. So let's draw the elimination reaction first. So I'm going to put the double bond here. And so that would happen because we have it in methanol, we have a strong base, and we have a good nucleophile. But because of that good nucleophile, we have to look at that other product. And if we use this as a nucleophile and displaced that, it's going to be an E1. So we're actually going to end up with our oxygen carbon bond, and that's going to be CH3. So we're going to have a mixture of both products. Okay, because once you form that carbocation, it can go either way. It can go with elimination, or if it has the beta hydrogens, because of that strong base available to it. And the last one, let's see, we have a secondary, okay, right here. This is a secondary. Ooh, we have acetone. That is not a protic solvent. So we're not going to go E1 or SN1, which means we're going to go SN1, SN2, or E2. So let's figure out what the products would be for that SN1 and first. The SN2 is going to be, let's see, hydroxide is going to come and displace the chloride, which means we're going to get a stereocenter inversion. We're going to talk about more what stereocenter means later, which means the hydroxide has to come in from the top to kick out the chlorine. So we're going to have a solid wedge for that OH if it did the substitution reaction. And let's draw our alpha hydrogens here and here. Those are going to be the same. So our double bond is going to end up inside the ring for our beta elimination product is going to be like that with our methyl group hanging out there. Okay. So you're starting to see a pattern and a way to attack these problems. Okay, so I think whoa, there. Let's go back to this table again. Okay, so whenever you have that SN2 reaction, never occurs. We have weak base, good nucleophile, it does the substitution reaction. Strong base, good nucleophile, it does the elimination reaction. So in our last example here, right here, which is going to be our major product for this one right here and this one right here, okay? They are both strong bases, but they are also strong nucleophiles. So when we want a nucleophilic substitution reaction, we want a weak base strong nucleophile, which means our major product on both of these is going to be the elimination product for both of the examples. Okay, questions?
I'm a little lost on how you place the double bond for the last one for the elimination.
Okay, yeah, let me, now that we've seen that, I'm gonna go ahead and erase a couple of these and redraw the starting material. Come on, there we go. Let me redraw the starting material right here now. And we have the solid wedge there. We have the dashed wedge here, chloride, right? And we have our beta hydrogen and our beta hydrogens over here, okay? So what we will be doing is we're going to have to take, we're gonna, if under an E1 or an E2 mechanism, we're gonna remove one of these hydrogens, they're the same, so I'm just gonna choose the one on the top. And when it does that, the electrons from that bond kick in and the electrons from this kick out, giving us our chloride ion. And notice where the double bond ends up. So the final product has that double bond with only one carbon in between the substituent and that double bond. Okay, so let me redraw the product. With a double bond there. Does that make sense where the double bond is now?
Yeah, I just think you drew it differently than the first one. That's why I was confused.
Yeah, I think I flipped it, unfortunately, so that's why I redrew it. Thank you for clarifying. Okay, so that is the end of chapter 7, okay? So I want to actually end here. I want to do all of chapter 6 all in 1 week because it's kind of hard and I want to get your undivided attention for those 3 straight days so that we can do it correctly. But what I can do now is I can actually pull up the review for chapters 1 through 5 actually, and we can start the review today. And we can, or you can just go ahead and, do we want to start the review today or do we just want to have a little extra time to do homework? Okay, there's 19 of us here, we can vote. Okay, well, why don't we do this? Why don't we go ahead and end here. On Tuesday, we're going to start with just chapter 6. We're going to do chapter 6 for Tuesday and Thursday. And then on the following Tuesday, we'll have our review for our first exam. Okay? Good. All right. All right. If you want to stay behind, go ahead and ask questions.